Today we are also in section 3.2 again. This is the second day in the log chapter. So to kind of go back to yesterday and evaluate, we're just going to kind of discuss some new properties. So here I have log base 7 of 7. So if I raise 7 to the x power equal to 7, I get that x equals 1. So log base 7 of 7 is equal to 1. Over here, I have 5 to the x equals 1. And the only way to get the answer of 1 by raising something to a power is that x has to equal to 0. So 5 to the 0 power is equal to 0. So to kind of formulate these two, these are special properties about logs. So if my base and my argument are the same, it will always equal 1. And if my base and the argument is 1, it will always equal 0. So those are just, like I said again, two properties about them. So now we're going to discuss two more properties. So if I were to evaluate these, so we know I set it equal to x. So I would say 4 to the x power is equal to 4 to the 5th, which means x equals 5. Which means this whole thing, log base 4 of 4 to the 5th, is equal to 5. Over here, I would have 6 to the x equals log base 6 to the 9th. And I know that this piece over here, I know that 6 to the x power equals 9th is what this right hand side is saying. So notice I have 6 to the x, 6 to the x, therefore the answer is 9. So this is equal to 9. So this again is just two more properties. And again, it's not that you have to memorize these properties, you'll find that it always works, but just shortcuts. So if I have log base b of b to the x, it'll always equal x. And if I have b raised to the log base b of x, it will always again equal x. So again, just two properties. You can always figure it out though if you forget the rules. So next thing we need to discuss is our common log. So one thing that you need to know is log has a base of 10. So if you never see a number written there in this little base spot, it's implied that that value is a base of 10. So now we're going to do some word problems. So it says the magnitude R on the Richter scale of an earthquake of intensity I is given by R equals log of I over I naught, where I naught is the intensity of barely felt zero level earthquake. The earthquake that destroyed San Francisco in 1906 was 10 to the 8.3 times as intense as a zero level earthquake. What is the magnitude on the Richter scale? So this statement right here is what we're going to plug in for I. So it's saying it's 10 to the 8.3 times the intensity of the zero level intensity. So now we're going to go into this formula, and it says R equals log. In the numerator, I'm going to replace I with 10 to the 8.3 I naught over I naught. They're going to cancel out, so now I'm left with R equals log 10 to the 8.3. And remember, it's implied that log has a base of 10, and if we use those properties, whenever the base and this value is the same, the answer is just the exponent. So the answer is an 8.3. So the magnitude of the earthquake in San Francisco was an 8.3 on the Richter scale. So next example, when the outside air temperature is anywhere from 72 degrees to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The bar graph in the figure 3.16 shows the temperatures increase throughout the hour. The function f of x equals 13.4 ln x minus 11.6 models the temperature increase f of x in degrees Fahrenheit after x minutes. Use the function to find the temperature increase to the nearest degree after 50 minutes. How well does the function model the actual increase shown in the figure? So one thing that we need to jot down that we didn't jot down is that the base for a natural log is e. So we typically never write the base for natural log. It's always implied to be e. Log is only base 10 when there's nothing written there. Otherwise, it could be a different value. So for here, I have f of x equals 13.4 ln, and I'm going to evaluate this at 50 minus 11.6. Now this is just a bunch of calculator work. You would use the calculator to figure out ln of 50, times it by 13.4, and then subtract 11.6 from it. When you do that, we get an answer of approximately 41 degrees. And the question says, find to the nearest degree after 50 minutes, which we did, and it says how well does the function model the actual increase shown in it below. So we were only off by 3 degrees. So I would say that this function models the actual increase fairly well. So we're going to do some more practice on calculator work tomorrow and some word problems.